Hello students and welcome back to Chemistry A. This is Miss Sleight and today we're going to be talking about experiments and data analysis. So we're going to start with experiments and we're going to start by talking about our three main types of variables. So in every experiment you have your independent variable, which is the variable that is manipulated during the experiment, meaning it is what you are directly changing. And that's always going to be graphed on the x-axis of your graph. Next is the dependent variable. This is the variable that changes in response to the independent variable. So it's kind of like you're changing the independent variable to see how it will affect the dependent variable. The dependent variable is always graphed on the y-axis. And I kind of have a little saying to help me remember this, and it's, why you so dependent? Because that's how I remember dependent variable goes on the y-axis. Why you so dependent? Then lastly, you have your controlled variables, and that's just anything that's kept the same during the trials of your experiment. Because again, you really only want to be testing two variables at a time. Also with experiments, we make a lot of observations. Observations come in two types. There are quantitative observations, and they are ones that deal with numbers or measurements. There's always a number associated with a quantitative observation. Examples of quantitative observations are things like mass, volume, density, length. All of those involve a number. On the opposite side of that are qualitative observations. Qualitative observations are ones that don't involve numbers. So there's no numbers, but we're still using other descriptors to describe what's going on. Because a lot of times important things happen in an experiment that aren't necessarily specifically measurable with a number. Examples of qualitative observations are things like color, texture, shape, odor, and you could go on with the list. Once you've kind of done your experiment, you've set up your variables, you've collected your data, the next thing to do is to graph it. And first off, scatter plots, as shown below, are the most useful graphs for determining if there is a mathematical relationship between two variables. So in this class, when you are asked to make a graph, you are going to make a scatter plot. Again, remembering that on the y-axis, we put our dependent variable, and on the x-axis, we would put our independent variable. If there is a mathematical relationship between your two variables, like you can see in this example, the data points seem to go at a linear rate, you can draw a line of best fit, or a trend line, that shows the average of the data. In this class, we're going to be making trend lines if we appear to have linear data. And that trend line should always pass through the middle of the spread of points, like so. If it's a linear trend line, you're going to be asked to find the slope and write an equation for the line. The important thing to note, when you are finding the slope of your line of best fit, you need to use points that fall exactly on the line. These are not always data points. So you need to look for the intersections on the graph paper that line of best fit intersects, not necessarily what data points it goes through. And you should never make or force your trend line to pass through data points, because it will skew your slope. Now let's talk about uncertainty, because part of doing experiments and stuff is measuring. And measuring always has some amount of uncertainty. If we look at this ruler, okay, if we're measuring the length of this gray box, we can tell it's more than a centimeter. We can tell it's more than 1.3 centimeters. It's really close to 1.4 centimeters, but it's not exactly on it. So we need to estimate how close to 1.4 centimeters it is. And we do that by tacking on an extra digit. It's our estimated digit. In this case, the easiest way to estimate it is 1.38 centimeters. Now you might have thought maybe it was 1.39. That's also acceptable because that last digit, this one right here, that is your uncertain or your estimated digit. So that's something that might vary from person to person, as long as it makes sense. Like in this example, it would not make sense to say this is 1.31 centimeters, because it's clearly much closer to 1.4 than it is 1.3. Let's look at some more examples of identifying uncertainty and making measurements to the correct number of digits. So here we've got some graduated cylinders. One thing to keep in mind with graduated cylinders is you always want to measure from the bottom of what we call the meniscus, or the curved part of the liquid. So you can see we've drawn in some dotted lines to mark where the bottom of that curve is. That's where you want to measure from. You never want to measure from like up here. That's not going to be an accurate measurement. So if we look at our graduated cylinder on the left, we can see that it is going by ones for its markings. So we're above 35. It's a little bit more than 36, but not quite 37. So how would we estimate this? Well, it's clearly more than 36, but not quite 37. So we need to estimate the tenths place. And we could say it's like 36.4, because to me, it doesn't look like it's exactly in the middle of the two marks. But again, if you had something like 36.3 or 36.5, those would also be correct, because your estimated or uncertain digit can vary from person to person. Now, what if we're over here, like on this one right here? We are going by tenths for our markings. So this is clearly more than 3.5. In fact, it looks like it could almost be exactly on 3.6. Even if it looks like you're exactly on the mark for something, you still need to include an estimated digit. In this case, if it looks like something is exactly on the line, you make your estimated digit 0. So here it looks like it's exactly on 3.6. So we make our measurement 3.60. So take a moment to write down what you think would be the measurements for both the graduated cylinder on the left going by tens and the graduated cylinder on the right that's going by 500s. All right, let's see how you did. So the one on the left, I would call that 464. We're estimating the ones place. But if you had 465 or 463, those would also be correct. That estimated digit can vary. The other one, I would estimate that to be 300s, because if we're going by 500s, our estimation is occurring in the hundreds place. And it doesn't look like it's exactly halfway between 500 and 0, so I called it 300. If you had something like 400, that would also work, because again, the estimated digit is the one that's going to vary. And in this case, it's the hundreds place. So again, always remember, you're always going to need to have an estimated or uncertain digit, which means you always need to measure one place past the graduations listed on the equipment. Every measurement has at one uncertain digit. Lastly, let's talk data analysis. So the first kind of two things we need to talk about when we're talking about data analysis is accuracy and precision. Accuracy is how close a measurement is to the desired result, while precision is the reproducibility of a measurement. So one of the easiest ways to kind of illustrate these topics is with bullseyes, okay, and like archery. So if we look at this one on the far left, one arrow hit the target exactly in the center. That is accurate. On our second one, though, none of our arrows hit the center of the target, but they were all grouped really close together. So in this case, they weren't accurate because they didn't hit the target, but they hit the same spot consistently. So that's precise. So they were precise but not accurate. In our third one, They were precise again because all of their arrows were in a tight grouping, but they were also accurate because they hit the center. Our last one, however, none of the arrows hit the center of the target and they are all spread out all over the place. So this last one is an example where the archer was not accurate, nor were they precise. So let's look at some examples of what we're going to see in class and on tests for what this will look like. First off, you have a series of close measurements are made prior to zeroing an electronic balance. Well, if they didn't zero the balance, you can't count on those being accurate. However, if the measurements were made really close together, they are precise. Our second example says the accepted value for the density of water is 1.0 grams in a cubic centimeter. The following experimental measurements were made: 1.0, 1.0, 1.0, 1.0, and 0.99 grams per cubic centimeter. This is an example of being accurate and precise. Almost every single time they dead on hit the accepted value, and all of their measurements were very, very close together, if not exactly the same. The last thing I want you to put in your notes on data analysis is the equation for percent error, because it is going to come up again. It is going to come up on the test. So while we have talked about it in class already, you're going to want to get this equation into your notes as well, so you can have it for studying. And that wraps up our talk about experiments and data analysis. Take care, and I'll see you in class.